This is section 16.1 on vector fields. We're going to see this is going to be quite a bit different than the recent material on triple integrals. But we will actually come back in a few lectures and start integrating in yet another context, not a double integral or triple integral, but something called a line integral. And to get there, we actually have to talk about these vector fields first. And so the basic idea is what I have written here, that vector fields can be used to describe really anything for which a magnitude and direction can be assigned to each point in some 2D or 3D region called the domain of the vector field. So really we're just talking about any function, right, that takes inputs of positions in the 2D or 3D domain region and outputs a vector for each of those points. So let's look at some examples of these sorts of things. Some quick examples. Some examples of these include velocity fields. The idea here is imagine, say, any point in an ocean or a body of water. At every point, there is some direction the water's flowing and some speed that it's flowing in that direction, right? These currents, even under the surface, the water's always moving somewhat. You could describe the velocity of the fluid at any point inside the fluid by a velocity field, right? At every point inside this body of water, you can draw an arrow in the direction the water's flowing there and with a length representing how fast it's flowing. So you can imagine that. The same works for not just liquids, but other fluids, atmosphere, right? Gases, things like this. Another common one is force fields. Gravitational forces. If you have some very large gravitational body, some large mass, well then at every point around that you can assign a vector that points in the direction that mass exerts a force in, and having a length representing the size of that force, how big it is. Right, so you could think of gravity, magnetic fields, electric forces. Right, there's gravity. Wow. Gravity. Let's get that right. Okay. So there's lots of different forces, and you can describe force fields for those. So I want to talk about one example of that in particular. I want to talk about the example of, for example, if I have like the sun at the center of my coordinate system. I want to draw just a rough sketch of maybe a representation of the force field, the gravitational force field due to this gravitational body, the sun at the origin. Well, gravity follows an inverse square law, meaning if I go say 1 unit out, whatever these units are, aren't so important, but if I go 1 unit away from this object in all directions, there's some force that this is exerting, and it's pulling in the direction of the sun. So I'll draw these arrows here saying that at any point on this circle here, the force is equal in all directions and pointing back toward the sun from all directions. Now this inverse square law says if we double how far away from the sun we are, so draw a circle of double that radius, then all points along that circle feel not half the force, but 1/4 of the force. We'll try to draw those 1/4 as big as the previous vectors. So we can state this inverse square law maybe more mathematically by saying that One way to say it is doubling the distance between objects reduces the force, the magnitude of the force, by a factor of 4. In general, increasing the distance by a factor of n decreases the force by a factor of n squared. Right, this is just saying that the force is proportional to 1 over the distance between the objects squared. This is called an inverse square law. I wanted to bring that up because we're going to do an example later that will come back to this. But now also maybe we can start imagining these vector fields as representing just a bunch of arrows all distributed out through your space with different directions and lengths to them. So now that we've got this stuff kind of parsed out, let's talk about a definition. We haven't seen a definition yet of what a vector field is. We've just talked about it in kind of loose terms. So I've got a definition here, and notice in black you'll see the 2D case, the case for a vector field defined at points in the plane. In blue, in brackets, I'll have the 3-dimensional case, case of a vector field that assigns points in 3D space a vector. Each of all these points gets its own vector. So the definition we're going with here is let D be a set in the domain, R2 or R3. In other words, if you're in R2, that's a planar region. It's a part of the plane. If you're in R3, that's a solid region. It's some 3D solid region. So you've got that domain D. A vector field on R2 or R3 in the 3D case is a function f with a vector hat on it. So we're saying this is a vector quantity that assigns a 2D in the 2D case or 3D in the 3D case vector called f of xy to each point xy in that domain. So it's just saying exactly what we said in words, but more mathematically. Every point in the domain gets a vector called f of xy or f of xyz associated with it. And this is just a function. Right? And I want to note, to draw this vector field, we saw a little bit of this up here, how we might draw a vector field. We sketch the vector as an arrow with its tail at the point where we evaluated the function, the vector field function, and given by a length equal to the magnitude of your vector field at that point. Right, so the direction and magnitude are important. The big idea here, though, is put that tail at the point that you're evaluating the field at, the tail of that vector arrow. So how do we represent these vector fields? Well, we're saying we call them something like capital F functions with a little vector hat on them. But in 2D, if we want to describe this vector field, we need to describe the components of it, right? The P and the Q functions here are just saying that our function is really a scalar function P in the I direction. So that's a vector I, the basis vector I, and scalar function Q in the J direction. Right, where P and Q both depend on X and Y, right? They can both change based on where we're at in the plane. But that field that we're describing is described by these two scalar functions. These are called component functions of the field F. And likewise, let's see if we can write down what it would look like in 3D if we had a function of 3 variables. Well, in that case, it'd be something like P of xyz now, and Q of xyz. And finally, we need another function because we're in 3 dimensions. Our vectors should be 3-dimensional outputs. We'll call it R of xyz as well. Right, that's P, Q, and R would be our component functions for this typical way to label our component functions in a vector field on R3. And before we get into some examples here, I want to note that we could write our input values, the x, y, z, or the x, y. We could write those as this notation right here, where I've written that input kind of as a vector, right? Vector field f evaluated at vector x really means the same thing that we write here, the usual notation. We're just thinking of this vector x as being a compact way of writing x, y, and z. So that x is just the position vector of the point x, y, z. So finally, let's see a couple examples here. I think these aren't too bad. We won't go into too much detail with our pictures because they're a little tough to do sometimes. But here we're given a field on R2. We're asked to sketch it. So I want to first see that what I need to do is actually decide some points where I'm going to plot this thing at. So I want a good representative sample of my field. I want to try to plot some useful points and see what the vectors at those points look like. So maybe I'll do a nice little grid. 9 points, I think we can handle that. Maybe I draw the vector at each of these points. So it's on a 1 unit scale here. 1, 0, 1, 1. 1, 0 out here, 1, 1 up here, 0, 1 up here, and so on. So if we want to just plug in those, we have to choose some points first of all. I'm choosing the ones I laid out there. Let me just write all these down, then we'll evaluate. I want f of, start at the bottom left corner, or the top left corner. Negative 1, 1, 0, 1, 1, 1, negative 1, 0, 0, 0, 1, 0, and finally the last one's down at the bottom, negative 1, negative 1, 0, negative 1, and finally I'll do it over here, 1, negative 1. I just wrote down those inputs to keep track of things. Now I'll sweep through here and just figure these out, right? This is 1, 1. I'm just plugging x equals the first coordinate, y equals the second coordinate into these components up here. It's as easy as that. Looks like this one is 1, 0. Looks like this one's 1, 1. Looks like this one is 0, 1. Looks like this one's 0, 0. Check this work, but I think these are okay. This is what I get when I do it. So I want to go through and I want to plot each of these. So for example, when I go to this first point up here, that was my first vector I evaluated. I just went from this point to this point to this point and just back down, right? So we'll go through these one at a time and draw them. So from this point, negative 1, 1, we want to draw the vector 1, 1, which goes over 1 and up 1 when we draw it. So that's our vector. It's as easy as this. There's really nothing to this. At 0, 1, I want to draw the vector 1, 0. So that looks like this vector. I'll make that thinner. At the next point, it's 1, 1. Back down here, the point we had is 0, 1. Or the vector we have is 0, 1. That's going to look like it doesn't go any amount in the x direction. It goes all 1 units in the y direction. The vector at the origin is just the 0 vector. It has no magnitude or direction. We can't actually represent that, so I'll just leave a blank space here. Jumping across to 1, 0, I need the vector 0, 1 again. Looks like that. Down here, negative 1, negative 1, I need the vector 1, 1. Looks like this. Down here at 0, negative 1, I get the vector 1, 0. And finally, at 1, -1, we get 1, 1. Right, so we get a rough picture of just what's happening near the origin. If we wanted more detail, we plot more points and more vectors. It's not so bad. You do want to notice, though, that the lengths matter. For example, these vectors, the ones that are at the diagonal, those have a longer length, I think length √2, compared to the vertical and horizontal ones we drew. Those ones have length 1. So make sure you do draw those lengths as appropriately as you can. I'll tell you, these pictures get real ugly really quick, so don't stress too much about sketching them nicely. More see what this is saying. If this was like a fluid flowing, we'd say that a fluid flowing in from this side kind of follows these arrows out and around the other side, right? Unless you're right on this line to the origin, it looks like you'll be deflected around the origin and keep on going. That's how we want to read these. Is most often, I think it's useful to think of these sorts of pictures when considering fluid flow. Right? How a fluid would flow through this region. These arrows, it always wants to kind of follow the direction of the arrows sprouting from where it's at. So let's see one in 3D. How do we do this in 3D? Well, in 3D, I just want to first acknowledge it's going to get uglier quicker. It's hard to make these pictures nice if I plot a lot of points like I did in the last one. But notice, in this case, this is a field on R3, but it's independent of Z and Y. So I say it's independent of Z because my thought is I know how to sketch a vector field on a plane. We did that in the previous example. So let me just sketch this in the XY plane, and since it's independent of Z, I'll get the same sheet of vectors at every height Z above the XY plane. So let me think of it this way. In the XY plane here, just looking down low in the XY plane, if I sketch some of these vectors, for example, 1 on the x-axis, 0 in the other directions, right there, the vector I get out is 1j, which is just a unit vector in the direction of, in the y direction, right? It's that guy. But if I move over here a little bit more in the y direction, well, this guy doesn't see any change, right? This only depends on x, so I get the same vector again. And I get that at every y value. Even the negative y values back here. Okay, so then if I go out, this is 1. If I go out one more unit, well, now look what my vector is going to be. I'm at x equals 2. If I plug in x equals 2, I'm getting the vector 2j, as opposed to the 1j I had before. So my vectors look like they have the same direction, but they're twice as long. And same if I go in the opposite direction. Okay. And I could keep going out to 3. They're just going to be 3 times as long. Right. These should all be straight lines if we could. Okay. And so on. And I could go in the negative x direction, maybe to x equals -1. And what will I get there? Well, at -1 for x, I get -1 times j, which is just the same vectors but pointing in the opposite direction now. And this is all in the xy plane. I haven't drawn anything. -2 will give me -2j. I haven't done anything in 3D yet. And so if I want to represent what this field looks like on R3, I can say, well, it looks like that in the XY plane, and I'll just not even try to draw it. Just say this repeats at each horizontal plane, z equals k. Right? If I wanted to see what was happening up in the z equals, I don't know, z equals 5 plane way up here, well, I know I'm just getting that same picture. not doing a good job of repeating my picture, but I think we get the idea, right? This picture in the xy plane is repeated in every plane at any height z. That's because this field was independent of z. So I think this is a nice way to handle these 3D fields if you're trying to actually sketch them. There's not much we could ask you to sketch nicely here, but maybe something that's independent of one or two variables. You could do it this way. Draw what it looks like in one plane, say it's the same in all the other constant planes of that variable that's missing there. Okay, so I'm going to go a little bit further here. Now might be a good time to pause, take a break if you want. We're going to get into some more conceptual stuff here. We want to talk more specifically about force fields. All right, all these vector fields we've talked about are useful, but what about force fields in particular? I want to look at an example here of coming up with a formula for the force field due to the gravitation between two masses. So let's consider the force on a little mass m, I've located it out here, located with position vector x. And let's consider the force on little m due to this big mass m located at the origin. I want to figure out what is that force field? Or let's just say it this way, what is the force on little m due to big M? Okay, so let's see. This isn't a vector field yet. This is just a single vector we're trying to describe, the force on this little m due to this big M's gravitation. Well, let's use this law of gravitation and say that the magnitude of a force is proportional to the product of the masses divided by the square of the distance between the masses. So if big M's at the origin, right away I can say divided by the square of the distance between the masses, that's divided by the length of this position vector squared. That's the distance between my two masses. Right. Oh, and I should be careful. We're saying the magnitude of the force. So the magnitude of this guy is this. It's proportional, though. I want to go back here into this proportionality statement. That just means when I see the word proportional in mathematics, I want to think this just means literally can be replaced with the words. Proportional just means is equal to a constant times. All right, so when we say this force is equal or is proportional to this product, blah, 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 we're really saying the force is equal to a constant times the product of the masses, da, 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 da. So if I plug in just some constant for gravitation, we use the gravitational constant, capital G, then I've turned this proportionality statement into an equation, right, is equal to. Okay. I shouldn't say equal here, I should say this is the same. So it's proportional, equal to a constant times the product of the masses. I'll be clear, this is my gravitational constant. The product of the masses, so that's little m times big M, divided by the square of the distance between them. We already have that here. So this is an expression so this is an expression for the magnitude of the force on the little m due to big M. Now, if we want the actual force itself, what are we going to do? We need to take this magnitude we know it needs to have. I'm going to stop writing this subscript here. We'll know it's implied. The force itself, though, is that magnitude multiplied on a unit vector in the correct direction. Right, we could always break up a vector into its magnitude times a unit vector in the direction of the vector f. So here, all I need to do is figure out a unit vector in the correct direction. Well, we go back to our picture and say, okay, if I'm little mass m out here in space, out here, and I'm experiencing gravity due to this guy, well, that gravitational force is pointing back at the origin, which, if we look at this, is just the direction opposite of vector x, right? Back at the origin is opposite of this vector that goes from the origin to m. So we can say this unit vector down here, should just be, let's say this unit vector is just negative the direction of x. And to make it a unit vector, let's go ahead and divide by its own magnitude. So let's see what we have. We have the magnitude of f is really g little m big M over magnitude x squared. And we have negative x vector over the magnitude of a negative x, but that's just the magnitude of x, right? The negative doesn't affect the magnitude. So let's gather it up. We have negative, usually it's written mmg over magnitude x cubed if we put all the powers together, times this x vector. So that's saying if I'm at this little mass's position x in space, then the force I feel due to this little guy is equal, due to the mass of the origin, is given by this vector expression here. But notice different masses vary here. We'd like a description of the force experienced due to big M without having to have a little m in there. And so when we want that, this doesn't really do it. This is too specific, right? This tells us the force experienced by a very particular force little m. So what we often do is we want the gravitational force field due to big M at position x. We'll call this F grav at x, but the idea is it should be some expression of this force that's being experienced, except you don't want to include the fact that you used this little test mass, this little m, to come up with this formula, right? It involves that little m there. So what we instead do is we say, okay, just divide the actual force experienced on little m by big M. Just divide that by the mass of little m. That takes out all the dependence on that mass. Then we can say this field is just dependent on the big mass that's exerting the field, the gravitational force, and the position you are in space around it. If I want to figure out the actual force I experience at that position, I can multiply the field by the mass that I have. If that's little m, then multiply in the little m, like we had before, and you get the specific force experienced at that point due to big M. So here is, I'll put this together and put a box around it. This is something we're going to use again later, this gravitational force field. This is nice. Due to mass big M at the origin. That's what we would call this formula. And remember that G there is just a constant. It's called the gravitational constant. Okay. So it might be strange that we have an inverse square law, but that we're actually dividing by the distance cubed in this field. Remember that one of those distances came from just normalizing, bringing the size of this direction vector x into control, and then dividing by the square of the distance between the observer and the big mass m. So it might seem weird to have a cube there, but it is correct. It is correct. So let's go a little bit further. I think this is the last big topic of this section, the gradient fields. The idea here is that we've actually already seen some vector fields. If we think back to these scalar functions, f of xy or f of xyz, we talked about an operation we can do to those that outputs a vector filled up with their partial derivatives. That was called the gradient vector. Gradient f of xy is just a 2D vector filled up with fx at xy and fy at xy. So this is just a field. This is just a vector field with component function fx in the first slot and component function q of xy equals fy, right? So it's just a vector field where these functions of x and y happen to be partial derivatives of our original function f. Same thing for a gradient field for a function of 3 variables. This is just a vector field on R3. What we want to know is that that vector field everywhere in R3 points in the direction that your function increases the most rapidly. The length of those vectors represents how fast it increases in that direction. And go back to the section on gradients to remember that. So let's see a nice standard sort of gradient field problem. Let's plot the gradient field of this function, f of xy equals x squared plus y squared, along with a contour map. So let me do the contour map first. You might have noticed I switched to blue ink here. I'm not sure why. One of life's mysteries. Okay. That'll work. Good enough. Doesn't need to be perfect. So if I want to sketch a contour map first, that means setting my function value equal to several different constants and sketching the curves that those give me. So for example, if I plug in k equals 1, I get 1 equals x squared plus y squared, which is just the unit circle. Oops. Just the unit circle. Good enough. Okay, so that is unit circle. And so this I would label with the function value is 1, maybe we would just label it with a 1 on it. Now if I increase the function value to 2, let's even make it different. Let's make it let's choose a convenient value, k equals 4. So when I plug 4 in here, I see that my radius is actually doubled what my radius was before. Radius 1, now radius 2. Tricky to draw this correctly with a computer. Okay. Good enough. So say we stopped there. Say we didn't even work out more contour lines. That's fine. Usually we do at least 3, so maybe you do one more. K equals 9 would be easy. But I do want to label this one with the function value 4 so we can see that we increased our radius, we doubled our radius, but our function value quadrupled here. So if we did another, we'd just get a bigger circle outside of that. Radius 3 would have a function value of 9 on it. Those should all look like concentric circles of integer ratio increases between them. Integer ratio increases of radius between them. Now if we look at the gradient, remember that's just the vector filled up with partial derivatives, so 2x and 2y. Now if we plug that in anywhere, remember we could actually plug in values. We could plug in like, I don't know, 1, 0 and get out the vector 2, 0. We could plug in a bunch of values and plot this. But what a problem like this is really asking about is to show the relationship between the gradient field and the contour map. Remember, we've seen this before. Anywhere where I plot the gradient vector, it's going to look perpendicular to the contour line where it was created. You might say, okay, well, perpendicular is fine. How do I know it's going outward and not inward? How do I know it's not going inward like that? Remember, the gradient always points in the direction of increase. And having this function value out here at 9 is an increase from 4 where we're at. So we have to go outward towards that direction. Right, but we saw a little bit about this before, so I don't want to stress the point too much. You might want to do something like this. I would say there's one issue with how I've drawn this, and that's that the vectors aren't getting bigger. Notice our gradient has a magnitude of 4x squared plus 4y squared, which is 2r if we were to switch over to polar coordinates. This is just telling us whatever distance we are from the origin, the radius should look like double that. So maybe I fix this. Maybe I fix this. Twice the radius that I'm currently located at. I'm located at a radius of 1. I need to go 2 units away. Still orthogonally though. I'll just extend those guys. Well, if I'm out here at 4, how far out would this extend? This would extend 8 units, which is probably something like way out here. So I don't know that we necessarily need to do that, but you might see why I wasn't worrying too much about getting these lengths perfect. They're going off our page. But you do want to pay attention to them in general when you're sketching these. Okay, so that's it for this example. The big thing to keep in mind here is when you sketch a gradient field along with the contour map, you want to show these orthogonal relationships between the vectors and the level curves. Okay, here's our last little definition and exercise here for this section. This definition is going to be very important to us going forward. So please be sure to think hard about this, try to understand what it's saying here. A vector field F is conservative. That's what we're defining. We're defining what it means to be conservative. A vector field F is conservative if it is the gradient of some scalar function. In other words, if we can write our vector field as the gradient of some little f, some scalar little f, then we would say F is conservative. Not all vector fields can be written this way. There are vector fields that are not the gradient of any scalar function. If there is a scalar function whose gradient gives you the field, right? If the field's conservative, then we call that scalar function whose gradient gives you the field. We call that the potential function for F. And so notice what we've said in the past. We'll do this example, but I want to think pretty critically about how to consider what conservative means. I claim that conservative almost means that this field is somehow some sort of anti-differentiable. Because remember, in past lessons when we talked about the gradient, we said gradient serves as kind of being like a derivative, like an overall type of derivative for a function of multiple variables. Right? We don't actually have an overall derivative. There's a partial in one direction or another, or a directional derivative in a particular direction. But an overall rate of change is hard to describe for a function of multiple variables. What's it with respect to? Which variable? So we said this gradient kind of accounts for all the ways it can change in the x, y, and z direction. So it sort of fills in as an overall type of derivative. I think this is a great way to consider it because now we're saying if something's conservative, under this sort of thinking we were exploring, this is like saying it's the field is anti-differentiable. Because think about what anti-differentiable meant for a function of one variable in Calc 1. We said, let me say it this way, we used to say f of x is anti-differentiable if you can integrate it, right? If you can actually figure out a function little f whose derivative gives you this thing back, right? Who is the antiderivative of capital F. But remember, all that statement meant is that the derivative of little f gave you back big F. That's exactly, shouldn't put the vector hat there. That's exactly what we're saying in this higher dimensional setting, right? F is anti-differentiable meant that we could find a function whose derivative gave you f, gave you the capital F function. We're doing the same thing here. Capital F is conservative if you can find a little f function whose kind of analogy for a derivative equals the field. Right? We don't really have an f prime now, but we have a gradient of it to take its place, and it's all kind of fitting together the same way. I encourage you to think this way about conservative fields. It's going to be very useful later to understand that sort of perspective. Well, like I said, this little f function whose gradient does give you back the field, that's called the potential function. That's a potential function for capital F. Just like there's many antiderivatives for a given function, you can add any constant to it. Same thing for these guys. Okay, so let's take a look here. This last example, let's ask, is the gravitational force field conservative? I'm giving us a hint to get started here that maybe we should consider if this function f of x, y, z equals capital mg over r, where r is given by this expression, is that a potential function for the field? Well, let's go back and remember this F-grav, this gravitational force field, right? We had this expression for it. Say it this way. That was our field, right? Well, notice this guy right here, this is magnitude of vector x. So let's just remember that. We'll put a pin in that for now and just remember that for later. But this is really just like an r cubed down here. So it's not unbelievable that these might be related, this guy and this guy. Right? It's the same sort of objects. So let's see. If that little f function satisfies that its gradient equals the gravitational force field, then we will know by definition the gravitational force field is conservative, right? It will have a potential function. There is a potential function that exists for it. So if we can prove that this little f function satisfies that its gradient is the field, then we will know the gravitational force is conservative. Gravitational force field is conservative. So let's see if we can do this. I want to take that f function and see what its gradient gives me. We're seeing if it gives us back the field we have up here. So let me take this little f and compute its gradient, which would just be, right, this would just be fx, fy, fz. That's the gradient. But this is fr times rx, fr times ry, and fr times rz, where r is this quantity here, right? I'm just thinking of f as depending on r, but r depends on x, y, and z, so this is a chain rule problem. If I want to know how f depends on x, I need to know how f depends on r, then how r depends on x, and so on with the other variables. This is nice, though, because it simplifies the problem dramatically. Fr can come out now, and now I see what I really have in front of me. I need to compute the gradient of little f. I need the partial derivative of f with respect to r, which is easy from here. Check my work, but that's an easy little derivative. Times this vector. And let's think about what that vector is. Well, that vector is just filled up with rx, ry, and rz, the partial derivatives of this r quantity with respect to x, y, and z. So I'll compute those down here. Partial derivative with respect to x looks like it's going to be x over the square root of x squared plus y squared plus z squared, which notice is just x divided by r. Check this. This is a step to check. I mean, I took it quickly, so check this. But I think you should get the same result if you're very careful with a single partial derivative chain rule there. And notice this r function that we started with is symmetric in x, y, and z. We could interchange those variables. We wouldn't know anything changed. So that tells us we have a very easy way to compute the other guys. We get right away, by symmetry, ry is y over r and rz is z over r. And again, you can check these if you don't buy it. Right? They're pretty easy to compute. Same way we did this one. So it's easy to plug these in. Rx up here is x over r. Ry over here is y over r. And rz over here is z over r. All that stuff inside that vector is being divided by r. Every component is. So I will bring that outside and divide the scalar out front by r. And let's see what we have. Keep in mind, where were we up here? Yeah, here we are. This r value we started with is just the magnitude of vector x, where vector x is the position vector of x, y, z. It's just x, y, z in a vector. So this r down here is really magnitude x cubed, and this is precisely vector x. Now notice, this is exactly the same. Let's connect it. This is exactly the same. We can weave around it. It's this guy, right? So we have shown this force field does satisfy that the fact that there is a, I should say it this way, this force field, for this force field, there is a scalar function little f whose gradient equals the force field. This little function, this is the gravitational potential, mg over r. So let's write that down. The gravitational potential, well first, yes, since there exists an f function such that the gradient of little f equals the field, we know the field is conservative by definition. By definition, if it has a potential function, it's conservative. The potential function we found is this expression we started with. Right, so it's saying the gravitational potential is really just a scalar function that takes the mass of the object emitting the field, the object exerting the force, times the gravitational constant divided by the distance from the object. Right? Somehow when you do that, taking the gradient of this guy gives you the actual field that's a vector quantity that always points toward the object and has the right inverse square law for the size of that force. You can check this. You can check that the magnitude of this force satisfies the inverse square law discussed earlier. Something to check out. Okay, that is it for the basics of vector fields. In the next video, we're going to go on to a couple of calculus operations we can do on vector fields that have some pretty useful significance. In particular, one of these called the curl. We'll come back again later in the term, later in the lectures that are coming down the road. So stay tuned for those next videos.